Hello, everyone. Welcome to our presentation in ICRA 2023. I'm Yanpei Huang. This paper is about using foot gesture and interface to control the grasping of a surgical robot. Many surgical tasks require 3 or more tools working together. Our hands-free interface could extend the surgeon's actions to control a third surgical tool and enable solo 3-hand surgery. For example, we have previously developed a foot interface which can collect fold-off foot motions to control one of the robotic manipulator of a surgical system. When foot control working together with hands operation, one surgeon is able to control 3 instruments simultaneously, avoiding the communication issues between surgeon and their assistant. However, most of the current hands-free interface don't allow skilled control grasping, which is critical to robotic manipulation. In this work, we systematically identify intuitive foot-machine interaction strategies for grasping control. We first selected 6 foot gestures. A survey was conducted to investigate the difficulty of them. 3 modular interfaces were developed to collect those gestures, followed by an independent control study. Eventually, the potential gestures were evaluated with a virtual surgical simulator. The initial 6 foot gestures are: first, metatarsal pressing, big toe pressing, toe extension, toe flexion, toe abduction, foot arch curl. They were selected based on analysis of foot biomechanics and the literature. 32 participants joined in the first study. They were encouraged to try the 6 gestures and then fill out the questionnaire by marking the difficulty of performing those gestures, and also select their top 3 to control grasping. The results show that participants felt toe abduction and foot arch curl are difficult to perform. These 2 gestures are also least preferred for grasping control. Based on this result, we removed these 2 gestures from our list and continue to study the others. 3 modular interfaces were then developed to collect continuous foot pressure of the remaining 4 gestures. The first interface was developed to collect pressure at the big toe and the first metatarsal. The position of the sensors can be adjusted based on foot anatomy. Once the sensor is located at the proper position, it can be fixed by the locking mechanism. The second interface was designed for toe extension. When using this interface, the toe extension rotates the mobile part towards the top plate and the pressure sensors. Third interface was developed based on toe flexion. The toe flexion rotates the mobile part towards the base and exert force against the sensor on the base. With the developed grasping interfaces, we continue to study the coupling effect between the proposed grasping foot gestures and foot motions. 6 participants joined the second study. They performed the virtual grasping task and motion task using a pedal interface and proposed grasping strategies. The grasping task was designed to record the foot motion disturbance while performing grasping. The participants were asked to control a virtual gripper to grasp an elastic ball on the screen with proper force. The foot motion disturbance was recorded by the pedal interface. Conversely, the motion task aimed to examine the foot pressure disturbance while performing foot motions. The participants were asked to move the pedal from the middle to 8 specified directions. The noisy pressure was recorded through the proposed grasping interfaces. In the grasping task, the motion disturbance was obvious on theta axis, which corresponded to the pedal pinch rotation, especially when using first metatarsal and big toe pressures to control the grasping. The result of the motion task show that the foot motion, especially foot planar flexion, obviously affect the big toe pressing, but has nearly no effect on the toe extension and flexion, which is not plotted in the figure as the value is too small. So we finally evaluated the toe extension and flexion with a user study of 12 participants. They are required to control the movement and grasping of a virtual laparoscopic tool in a picking and placing task with a surgical simulator. The results show that toe extension and flexion has similar performance, but most participants still prefer toe extension and interface 2. In summary, we have developed 3 modular foot-motion interface for grasping control, which can be easily integrated with motion control interface. I also proposed the systematic selection process to identify effective foot interaction strategies for grasping control of a surgical robot. Thank you very much for your listening. Please find more information in our paper. If you have any questions, please feel free to contact me.